Right. Okay. The last few weeks, what we did, we covered rectangular portrait frames, and this week and next week we are going to cover pitch roof frames. Yeah. So we are looking at pitched roof frames. Okay.
Hello, sir. Sir.
Yes.
Could you screen share?
Huh?
Screen share.
You can't see my screen?
Yes, I can't
Oh,
see
you
it.
don't? Okay, let me see. Oh, sorry. 1 minute. Can you see it now?
Yes, sir.
Okay, thank you. Okay. So pitch roof frames. So we're looking at frames where the roof is pitched. For example, in aircraft hangars, in warehouses, where you have got the frame with the roof at some angle. Okay, and they are a little bit special than the rectangular frames. So and I think I might, let me see. I might start with the PowerPoint presentation, and then I will go back to the visualizer. So let me just get the file here. Yeah. Okay. So I'm going to start with the PowerPoint, and then I will go back to the visualizer. Okay. So you should be able to see my screen now with the PowerPoint presentation. Okay. So we are going to divide it into two sections. This week we are going to look at symmetrical frames. And next week we look at frames where the geometry is not symmetrical, and then we see what difference it does make. Okay, so what we'll do, we are going to learn about what is particular about frames. We are going to learn how to carry out the plastic analysis for a pitch roof frame where the geometry is symmetrical, and finally we are going to construct and interpret the interaction diagram, which is what we did with the rectangular frames, if you remember. Where if you have a frame where the load is unspecified, then we can construct the interaction diagram to give us all the possible collapse mechanisms. So we have symmetrical frames like here. We have asymmetrical frames where the geometry is not symmetrical. We also have multi-bay frames. You've probably seen this in practice. Yeah. So if you have a big warehouse where you have a multi-bay, number of frames connected together. So today we are focusing on this here, and next week hopefully we'll start looking at something a little bit more complicated where the geometry is not symmetrical. This is a typical symmetrical frame. I mean, my drawing is not very good, but it's okay. So this is a typical frame where we have the frame subjected to vertical load and the horizontal load. These are critical loads, okay? These are critical loads. So the lambda is already embedded into the load, if you see what I mean, okay? And when you apply a combination of vertical and horizontal loading, you get a number of possible mechanisms. The first one is a sway mechanism, which is due to the horizontal load here. So the horizontal load will push, in this case, the frame to the right, and that gives a sway mechanism, okay? The frame will undergo a simple horizontal movement, so therefore there is no hinge forming in the apex. This is, we call it apex, that's the top of the frame, okay? So in the apex here, there is no hinge forming because we have a simple horizontal movement, and the only hinges will form at A, B, E, and D. So we have hinges at A, B, E, D, okay? The other possible mechanisms that you get with the picture frames is that with the load V here pushing down, so with the load pushing down like this, what could happen is that this column remain vertical, straight, and part of the frame will sway. Part of the frame will sway, okay? That will give us this mechanism. So, okay? Yeah. So in this case, you've got hinges forming at B, C, D, and E, and there is no hinge at A because this column here does not deform. There is no, there is no rotation. There is no rotation of this column, and therefore there is no hinge forming at A. Come in. And obviously, then we have to consider the combination of these two here, which give us a combined mechanism of the part sway and the sway mechanisms. And in this case, this is a little bit like the rectangular frame where the hinge at B here will cancel. Why does the hinge cancel when you combine these two?
Hello, sir.
Sorry?
The angle is the same.
The angle is the same, yeah, but why does the hinge cancel? You see here,
Hello,
the
sir.
sway mechanism, can you see here? This column rotates which direction? Clockwise. This beam here in this mechanism, the part sway, this beam or rafter, we call it rafter, not beam, this rafter rotates which way? Clockwise, yeah? So the column here rotates clockwise, and the rafter here, BC, rotates also clockwise. And because they rotate in the same direction, so the angle will remain the same, and therefore there is no hinge forming at B. It will cancel when you combine the two together. Very much well what we had with the rectangular frame, if you remember, where when you combine the mechanisms, the hinge will cancel when the rotation of the members connected rotate in the same direction. Is that clear?
Hello,
so
sir.
We have exactly the same phenomena here taking place. Right?
Hello, sir.
Now we're going to take a specific an example and then with numbers and see how it works. Have you got any questions? Is it clear?
Hello, sir. I have a question.
Sorry? Online, yes, I can't hear you. Can you shout?
Yes, for the vertical load, it's supposed to be equal mechanism for the two columns.
I hear you very, very, it's not very clear.
I say for the vertical column, for the vertical load, it's supposed to be equal deformation for the two columns since the frame is symmetrical.
For the two columns here.
If it's symmetrical, the vertical load.
Yes.
It should
For
be
the
same
vertical load.
If it's symmetrical, what's to say?
The A, B, and D, E columns should sway the same way if it's asymmetrical.
If it's symmetrical, you mean the displacement here?
Yeah.
Of course.
Yeah.
Yes.
That's what he's asking.
Yeah, don't worry. We are looking at symmetrical this week. Okay, this is the example we're doing. And next week, we will do an example where the columns have got different heights, okay? And then we look at the geometry, okay? So let me go back to the visualizer now. Okay, so let's close. Oh no, sorry. So which one is it? No. Yeah, can you see the screen now, the visualizer? Okay, so what we have, the example we have is a symmetrical picture frame like this. It's fixed at the base. We have a vertical load V, horizontal load H. The height of the column here is 5 meters. And the height of the roof to the apex is 2 meters. And then in this direction, the bay, we have 8 meters and 8 meters for the horizontal bay. Okay. The MP is given. It's the same MP for all the members. Okay, so we have the same MP for all the members. Okay, so let's call this here A, B, C, D, and E. Okay, so now we define the number of possible hinges. M is the number of possible hinges. So we have one hinge at A, a hinge at B, possibly, and then we have a possible hinge at C, a possible hinge at D, and E. So we have a total of 5 possible hinges at A, B, C, D. Okay, A, B, C, D, E. Then we define the number of, the degree of redundancy, and the degree of redundancy is the number of unknown reactions. So we have 3 plus 3, 6 unknown reactions, minus the number of equations of equilibrium. We have 3 equations of equilibrium, so the difference is 3. Okay, so that's the degree of redundancy. Then we have capital N, which is the difference of M and N. In this case, 5 minus 3 is 2. This is the number of independent mechanisms. That's the number of independent mechanisms. So we have 2 independent mechanisms. What are they? What are the independent mechanisms? We've just said it. Sway and not combined. Part sway. Yeah. So we've got exactly what we expect. We expect a sway mechanism and a part sway, and obviously you need to check the combination of the two. Okay. N plus 1. Okay. N plus 1. In this case, 3 plus 1 is 4. So what is 4? Remember what is N plus 1? Number of hinges needed for what? For total collapse. So N plus 1 is the number of hinges needed for total collapse. So although we have a possible 5 hinges forming, we only need 4 for total collapse. Okay, so out of the possible 5, we only need 4 for this frame to collapse. Okay, so let's start with the analyzing each of the mechanisms, and the first one is the sway mechanism. So we start with the first one, which is the sway mechanism. So this is the frame here. This is the frame. Okay. Now when the frame sways, this is how the frame is going to sway. So this is how the frame is going to sway. Is that clear? So it's going to be pushed to the right, and that's how the new position of the frame. Okay. So we have A, B, C, D, and E, and we have the new the new positions, we have B dash, C dash, and D dash. And these are the new positions of the joints. My drawing is not very good because these two should be the same. Yeah, the displacement here must be the same because we have symmetry. If the angle here is theta, then the angle at the other side is also theta. And therefore this displacement here is the height 5 theta. So the displacement is 5 theta, and it's the same here, 5 theta, because this column have got the same height. We have symmetry, so this is also 5 theta. The other thing I would ask you to do all the time is to show the always show the hinges and the direction of the moment. So we have a hinge there, a hinge. Now, in this case, because MP is the same everywhere, so the hinge here will form exactly at B. But remember, if you have different values of MP, the hinge always forms in the weaker member. Yes? So in this case, it's there. Then we have a hinge at D, and finally a hinge at
Will it be between A and B if A and B?
If they have this different MPs,
Yes.
it will form in the weaker member. It will be at the corner, but in the weaker member. Okay? Yeah. We'll do one next week. Okay, we'll do. I got something that we can do next week. Okay, so we have MP there. That's the direction of the moment, MP. Then at A we have MP. At B, sorry, we have MP. Then at D we have theta here, and the moment is MP. And finally we have MP there. It's always from the
What
new.
of RC?
It's always against the rotation. Okay, whichever the member rotates, the moment will be opposite to that rotation. So for example, here the rotation is clockwise, so the moment MP is anti-clockwise, always. Okay, because it's a moment of resistance. It's an internal moment. It's an internal moment, and it's a moment of resistance. Okay? It's not an external moment. Okay. So, and that's it. Now we do the external work and the internal work equilibrium.
Sir,
Yes.
someone is asking me a question.
Sorry?
Online.
Online?
Yeah.
What?
I said, why is there no MPRC?
Sorry? My
Why
hearing is not
is there
very
no
good. You have to speak
MPRC?
louder. Sorry?
Why is there no MPRC?
Why?
Why is there no MPRC?
Because it's a simple sway. It's a simple horizontal movement. There is no, you can see here, joint C does not move vertically at all, right? It's a simple horizontal movement. So you have your frame swaying this way, and that remains at the same level. Okay? So this here, A, B, C, D, does not undergo any deformation. Okay? It goes,
Okay.
all we have is a simple horizontal movement, and therefore there is no hinge forming at C. Because it does like this, it goes like this, but the top here does not deform in any way at all. It's only the frames rotating, that's all. And carries with them BC. Is that clear? So there is no hinge, because it doesn't rotate. There is no rotation taking place at C. So we have external work, we have MP theta. So in external work, we have the H and V. There is no work due to V because there is no vertical displacement, but we have a work due to H. So we have H times the corresponding displacement to H, which is 5 theta, equals, we have MP theta at A, we have MP theta at joint B, we have MP theta at joint D, and finally we have MP theta at joint E, right? Which gives 5H theta equals 4 MP theta. Theta and theta cancels. So we have H is 4 MP over 5, which is, MP is given 50. So we substitute MP by 50 divided by 5, which gives 40. So the sway mechanism gives us a H equals 40. So a horizontal force here of 40 will give us a sway mechanism regardless of the value of V. Okay? Next one now is the part sway mechanism, where this column here remains vertical, and then we have a partial sway of the frame. So we have partial sway. So number 2, partial sway mechanism. So this is the frame initially. Okay, and then for the partial sway, what you have the column, the column here remaining vertical, and what we have something like this. Okay, and we have a hinge forming there, there, and there.
Hello, sir.
Yes.
Load due to this partial sway is due to, is it a load due to the vertical load?
Can you hear his question?
This sway, is it as a result of the vertical load or the horizontal load?
The sway
This
is the vertical load.
The
The horizontal load here, you can see that this part sway is due to the vertical load pushing down. Okay?
If there is a sway, that means it's a combined mechanism. If it's only the
When you
vertical
combine
load,
them, work together, we work together, H and V, okay? This part sway is due to V in this case.
Sir, since the building is symmetrical,
Yeah.
if you're having a point load at the apex of the building, it's not supposed to sway at this other side. Why is it bending towards one side? And both legs are fixed.
No. These collapse mechanisms, you can think of a lot of maybe different ones, but these are based on what people have seen in practice. Because you need to eliminate, there is no point doing other mechanisms that will not give you the critical load. These are the tested ones. These are the ones that have been tested to happen. These are the possibilities.
is this one combined with the horizontal load?
The horizontal load, in this case, is applied at this end, so it doesn't affect this partial collapse. However, if the horizontal load was applied at this end, it will have an impact. We will do this next week. Okay? So if H is applied at the other end, then it will impact because it's going to make the frame sway more in this direction. Okay? But in this case, for this example, the horizontal load is applied at B here, so the path sway is due to the vertical load V, pushing down. Okay. So we have A, B, C, D, E. So we have C dash and D dash.
Excuse me, sir. On this matter, on this part 2, is that the effect of the horizontal force and partial?
No, it's vertical. I've said it many times. The horizontal is applied here. This column remains vertical, so it doesn't have any impact. It's the vertical force pushing down, and that makes the frame swaying in this way.
So what the effect then is only by vertical force? Why not sway down only, and then splits to the two sides?
What do you mean split two sides?
When instead of the swaying to this side, if it's only affected by the horizontal force in the pitch, I think I was expected to be swaying, one of them in the other side and one of them to the side, because it's already on the head. the pitch. So it's going like this one.
What do you mean? You mean sway like this?
Yeah, because the pitch is like this one now. If I apply the force on the top, it's got like
No,
this
no.
one.
Think about it. If you have a frame,
Symmetrical.
if you have a frame and you apply a vertical force,
Yeah.
okay, and the horizontal, it can sway. But the other thing is that if this, when you apply vertical force, one of the columns could remain intact and the other one sway, so you have a partial collapse. Okay?
So we have effects of the horizontal force.
Yes. The two together is the combined.
Yeah, that's right.
That's the combined. That's the next one. That's the next one. When you have both vertical and horizontal together. Okay? Okay, so if we call the angle here theta, okay, if we call the angle here theta, then the angle at E will be different. Okay, will be different. So we call it beta, and we need to find the relationship between theta and beta. Okay, we need to find the relationship between beta and theta. So bear with me, because I want to show you the how you get the angle beta. So the way to get the angle beta is you extend DE like this. So extend DE, and then you extend the rafter BC like this. And the two will intersect at point I. Okay? So you extend ED, extend BC, and the two intersect at I. Then you join I to the new positions of the joints. So you join I to C dash like this, and join I to D dash. Is that clear? So extend DE, extend BC, gives you point I, and then you join I to C dash and B dash. And the reason we are doing this, because we want to establish the relationship between beta and theta from geometry, right? Now, this triangle BC-I is an isosceles. Do you agree? Because we have the same, it's 8 meters, 8 meters. So BC-I is an isosceles. In other words, BC dash and CI are equal. So therefore, this angle here is also theta. If you have an asymmetrical frame, we'll look at it next week. But this is because we have symmetry. We have 8 meters, 8 meters. That means these two here are the same. So therefore, you have an isosceles, and that's theta. Okay? Then, if you look at this triangle ICD. If you look at triangle ICD, this triangle rotates to IC dash D dash. Okay, so we have a rotation of triangle ICD to the new position IC dash D dash. You agree? So this triangle here rotates by an angle theta, and therefore the angle here is also theta. Okay, because you have the triangle rotating from this position, okay, to this position, right? The diagram is not very, because I didn't draw it to scale. But if you draw this to scale on graph paper, you will see that theta there and theta there are actually equal. Okay, all you need is choose a scale for your frame, do it on graph paper, and you can get the angles from, just from graph paper. Okay, so we have the same angle. Now we need to find the relationship between theta and beta here. Okay. Right, we need to know what is the length, this here ID, because we have DD dash is equal to DE beta. It's also equal to ID theta. Do you agree? Yeah? Okay, so we have DD dash is DE beta or ID theta. Right? However, we know DB, but we don't know ID. So I'm going to try and work out what is ID. How do we work out ID? It's simple. What you do, you draw a horizontal line here, horizontal line, Okay? Sorry? Draw a horizontal line here, and let's call this N, this point here, N. Do you agree that ICN, INC, and IDB are similar triangles? Do you agree? You agree that INC and IDB are similar triangles? Yes? So we have ID, or IN, sorry, IN over NC is equal to ID over DB. Agreed? IN we don't know, so IN. NC, do we know NC? 8. ID, we don't know ID, but ID is IN plus 2 divided by DB. What is DB? 16. So I have one unknown, IN. Yeah. So we have 16 IN is equal to 8 IN plus 16, and therefore we have 8 IN is equal to 16. So IN is 2. Okay, it's just pure coincidence that they are equal, okay? If you change the geometry, you get different values, obviously. So we can say that ID is IN plus NC, which is 2 plus ID, sorry, ND. So 2 plus 2, isn't it? So ID is 4 meters. Is that okay? So therefore, now I go back here to this here. So we have DD dash is equal to DE, which is 5. DE is 5. Beta is equal to ID for theta, and therefore beta is 4 over 5 theta, or 4 over 5 is 0.8 theta. So now we have a relationship between beta and theta. So beta here is 0.8 theta. Okay? If you change the geometry, obviously the spans and everything, obviously you get different values. Okay? So you got beta 0.8. Now I can, the one thing I haven't done here is to show the, I like to show the direction of the moments. So we have MP here, then this is rotating in this clockwise, so we have MP, okay? And by equilibrium, we have MP, and we have MP, and finally, we have MP there. Okay, this is beta. So now we can write the external equilibrium and the internal, the external work and the internal work. The external work, we have V times what? Times the vertical displacement. And the vertical displacement is 8 times theta. Okay? 8 times theta equals 2 MP theta at B. This is at joint B. Then at C we have MP theta and MP theta. So that's at C. And at D we have two members. We have member CD and member DE. So we have MP theta and MP beta. This is at joint D. And finally, for joint E, we have MP beta. MP beta, okay? All right, so therefore we have 8V theta equals 1, 2, 3 MP theta plus 2 MP beta, 2mp beta, and beta is 0.8 theta. So which gives me...
it's meant to be 4 mp theta.
Sorry?
Yeah, 4 mp theta.
I can't hear you. What's your question?
MP theta is 4 mp theta. 1 at B, 2 at C, and 1 at D.
Oh, so, yeah, 1, 2, 3, 4, yes. So we have 2 times 8, 1.6, 1.6 plus 4. So we have 5.6 mp theta. Theta and theta will cancel. So we have V is 5.6 times mp over 8, which is 5.6. mp is given 50 divided by 8, which gives, I don't know if you can check for me. I got 40 if you want to check it, please. 5.6 times 50 over 8. Sorry?
35.
Is that 35?
Yeah.
Oh, yeah, because 5.6 over 8 is 0.7 times 5, yeah, 35, sorry. Okay, so the sway, the path sway gives us V35. Now we're going to look at the combination of the two, and this is where you have V and H, both of them working together. So you have got a combination of the sway and the path sway, where you have got the V and the H, both of them contributing to the sway of the frame. So now we do combined mechanism. 3. Okay, so now we do the combined. So this is the frame. Leave some blank space here because we need it, okay? So leave a lot of space here, please. So this is the frame initially. Then when you combine these two together, okay, when you combine them, as we said earlier, because of the rotation of this here rotates clockwise, and this member here rotates also clockwise, they rotate in the same direction. BC and AB rotate in the same direction, so the hinge at B will cancel, and we are left with the hinges there. Okay, so what we have this. It's not very good. I want to do it nicely, sorry. Okay, so something like this, yeah? What you can see here, when you combine the two together, you agree with me? Do you agree? When you combine these two, do you agree that the displacement at D will be larger than the displacement at B? Yeah, logically, yeah, because we have got a displacement at B there, and then we have got these two together, okay? So combining, obviously, will give us a displacement at B here, sorry, at D, which is larger at the other end. That's because we are combining the two together, okay? So A, B, C, D, E. So we have the new positions, B dash, C dash, D dash. Okay, now if I call this angle here theta at A, and let's call the angle at this end gamma. And now we need to find the relationship between the angle at theta there and at the other column. So then I can use it for the external work, okay? And we have here V obviously and H. And you can see that for this combined mechanism, both H and V come into play. They are both contributing to the vertical displacement and the horizontal. Now, how do I find the relationship between theta and gamma? We use a slightly different construction diagram. So what you do here, you take, connect A to C and extend it.
So we are at the place of plastic hinge.
Sorry?
We are at the position of plastic hinge.
Oh, the hinges. I did say the hinges would be at A, C dash, B, and E. Okay? So we have hinges at A, C, D, and E. No hinge at B, it will cancel. And we have exactly 4 hinges, because remember what we said? We said 4 hinges for total collapse. Okay. So what we do now, we are going to join. So we join A to C like this, and you extend it. Okay? You join A to C and extend, and then join and then extend DE like here. And these two will connect at point I. So we intersect at point I. I repeat, you join A to C, and then you join ED, extend ED, it gives you I. This is just a construction diagram to help us with the geometry. That's all, okay? To find the relationship. Okay, so then what do? Now we take E and join it to C dash as we did before. So we take point I, sorry. I join it to C dash, and I join it to D dash. Then I join A to C dash. A to C dash. So we join A to C dash. Is that clear? Yeah? So I repeat, join A to C, extend it. Extend ED, the column ED. That gives you a point I. Then from I, join to the new positions, I to C dash, I to D dash, and then you join this to here. The reason we are doing this is this. If we start from the left side, from this column here, and we call the angle theta, what do you think the angle here is going to be? This angle. What do you think the angle is here? Do you agree that ABC, this, can you see this triangle? Triangle ABC? It has rotated to AB dash, C dash. By how much? By theta. So this has to be theta. Okay? Similarly, you know this, do you agree that IC dash A is an isosceles triangle because we have the same, yeah, so we have got AC dash and C dash I are equal. So we have an isosceles. So this is the angle is theta because we have symmetry of the frame. Clear? Now, if you look at triangle ICB, triangle ICB has rotated, ICD has rotated to IC dash D dash. And therefore this angle here is also theta. It's the rotation of the triangle ICD. So the only thing left now is to find the relationship, because everything else is equal to theta. So we need to find the relationship between theta and gamma here. And we are going to use similar triangles like before. So what I'm going to do, I'm going to draw a horizontal line from the apex here. I draw a horizontal line, and let's call this N here. Right? And then similarly, draw a horizontal line here. You know. Yeah. So do you agree that I and C and I EA are similar triangles? Do you agree? Do you agree that ICN and IEA are similar triangles?
Yes, sir.
Yeah?
Yeah.
So we have IN over NC equals to IE over EA. Okay? So therefore we have IN, we don't know IN. NC, we know NC. NC is 8. Okay? Equals IE, we don't know IE, but IE is IN plus what? What's this here?
5 plus 2, 7.
Yeah, plus 7. Divided by, what's this here? AE or EA? 16. That's it. So now we have 16 IN equals 8 times IN plus 8 times 7. Is it 54? Yeah?
56.
Sorry. Equals, then throw this to the other side, so we have 8 IN equals 56. So therefore, what is IN? What is 56 over 8? 7. So IN is 7. And therefore ID is 7 plus 2, which is 9. So ID, here ID is IN 7 plus ND, which is this here, which is 2 meters. So now we've got ID as well. Then we say that DD dash, displacement, this displacement here is ID times theta or ED times gamma. ID is 9, so we have 9 theta equals ED. What is ED?
Is 5.
5 times gamma. So what is gamma? 9 over 5 theta. What is 5 over theta? 9 over 5?
1.8.
1.8. So gamma is 1.8 theta. Right? 1.8 theta. So now we've got a relationship between the angle at this column, AB, and the column at the other side. As we said earlier, the displacements obviously are larger on this end. Now, what do you notice here? If you put these two together, look, can I have your attention, please? Look. This is the sway mechanism, and this is the path sway, right? For the sway mechanism, the angle at E is theta. Okay? And for the path sway mechanism, the angle at E is beta, which is 0.8. So when you add these two together, what do you get?
1.8.
1 theta and 0.8 theta is 1.8 theta, which is exactly what we've got here. So you can do this in the future. You don't have to do this in the future. You can use what we call the principle of superposition. In other words, when you combine mechanisms, you can actually add them up to get the angles. Is that clear? Yeah. So I did show it here that you can get it from first principles, but in the future, for the combined mechanism, you can use using principle of superposition. Okay, we have gamma is theta plus 0.8 theta, which is 1.8 theta. And that's combining the previous two mechanisms. And we find the same result. Is that clear?
Yes.
Yeah. And you save yourself a lot of time by doing this in future. But you need to mention that you are using principle of superposition. Is that okay? So now we've got the angles. I'm going to show the direction of the moments as usual. So we have MP there against the rotation. We have MP here. Okay. We have MP there for equilibrium. It will be opposite. Then I have MP and MP. Okay. And finally, we have MP at E in this direction. And these are the hinges with the respective plastic moments. Okay, now we can do the external work and the internal work. So for the external work, we have H times, what is the displacement here? Sorry? 5 theta, yeah. So we have H times 5 theta plus V times 8. The angle is theta. So we have V times 8 theta equals, we have, at A we have MP theta. This is at A. Then at B there is no hinge. At C we have MP theta and MP theta. This is hinge C. And finally, not finally, for joint D, we have MP theta and MP gamma. This is D. And finally, at E, we have MP gamma. And I'm going to, this is at D, E. And I'm going to substitute here gamma by 1.8 and then simplify to get the relationship. So let's do it here. So we have MP H 5H theta plus 8V theta equals 1, 2, 3, 4 MP theta plus 2 MP gamma. Gamma is 1.8 theta, which gives me 2 times 3.6 for 7.6. 7.6 MP theta. And then the theta and the theta will cancel. So we have 5H plus 8V equals 7.6 times 50, which gives, what is 5.6 times 50? 380. Thank you. 380. Right, so in summary, do you want a break? Yes? Yeah, okay, we can have 10 minutes, okay? And then we will finish this. So I leave the recording on, and we're having just like 10 minutes, okay? No, average is what Indian case. So what is it? Because I'll answer. Because why I said there is no staff because see, and here we will be taking 1/2 minus plus. So this is there is no unit. I'll tell you. Yes, sir. Yeah,
0610.
yeah, okay.
Not that age.
And see, for here, so this is 3W plus L by 3 theta is 2W into this distance. 2W. So 2W L by 3. I don't know
You don't have to.
how. It's
You don't have to. We can write that. So, but they are usually providing internship sometimes. the base.
Is there some issues? That's 6 times. That's sure. Sure. It's not tough, but it's yeah, it's just sovereign. Practice questions are okay. Comedy, they do things. I just come over and I can. John, not you. John. I will know his name is John. Yeah. Last time we carried out
Because we want to give it the same person daily when we and that is in the lobby. So everything is going to he is definitely not attending the lobby. If he can see this thing is maybe not What is all this? What is all this? I just wrote last connect 83, then exit EV.
First,
I just need to start on the exam.
how was it last?
Okay, let's continue. Let's resume this and finish it. So to summarize, for the sway mechanism, we have H equals T. For the part sway, we have V equals 35. And finally, when you combine mechanism, we have here 5H plus 8V equals 380.
It's not equal, sir.
Sorry?
Not equal.
It's 480.
480 or 380?
You know, when we calculated it, 40 times 5 plus 3 plus 5 times 8 is 480. Not 380.
So there's a problem.
You got 380.
Yeah.
It should be 380. Why 480? Where did you get 480 from?
No, 380.
No, not that one.
5H.
We substituted the H and the V.
380.
It's 380. The answer is 380, definitely.
Yeah, you should get 3.
So that's 5 times 40 plus 8 times 35.
They've put in the values of H
Put the
and
values there.
Sorry?
They've put in the values of H and V.
Yeah, but it's 380. The answer is 380, yes?
It's 4.
Yeah, it is 380. I don't know what you're talking about. 380, isn't it?
No, if you put in the values of 5H and 8V, then you get 480. So
Where?
they put in the values over here.
Where?
Over here. They've put these values.
Oh, no. Why? Why put these values? No. They are completely different mechanisms. You can't do that. You cannot do that. Okay. So we have H40, that's a straight line. V35 is a straight line. And here we have 5H plus 8V is linear. So I need 2 points to draw a line. So for H equals 0, it gives me 380 over 8. What is 380 over 8? Is it 47.5. Okay? And here, if you put v equals 0 into the equation, you get h 380 over 5, which is 76. Okay? So I need 2 points to draw this line. Okay? Now we are going to plot these three equations into what we call the interaction diagram. So here we have an interaction diagram. Interaction diagram. So we put v in the vertical direction, and we put h in the horizontal direction. Now, you can see that v goes up to 47.5, so about 50, okay? And h goes up to about 76, around 80, okay? So therefore I can now choose an appropriate scale. So h 10, 20, 30, 40, 50, 60, 70, 80. Okay, and vertical, so it goes up to about 50. So we have 10, 20, 30, 40, and 50. So this is my scale, right? Now, first of all, we have h equals to 40. H equals 40 gives this line. So we have h equals to 40. So this line here is h equal to 40. Okay, so h 40, this is the sway mechanism. Okay, then we have v 35. V 35 is, this is 35 here. Okay, and that's v 35. So V35, this is the part sway. So this is part sway. And then we have got this line here, the combined H0, we have 47.5, 45, 47.5, 47.5, and 76, 75, 76. Okay, and then you join the two together. Okay, so this is H, 5H plus 8V equals 380, which is the combined. And this is the combined, this is the interaction diagram for all three mechanisms together. So let's call this point here O. This is P, Q, R, and S. Okay? Now anything inside this border here, anything inside, gives a safe combination. So anything inside the border here, inside is safe. Anything is outside, obviously, is unsafe. Okay? Then we have the specific lines. PQ is the part sway. So PQ we have part sway mechanism. Okay. QR we have the combined mechanism. And finally, RS, we have the sway mechanism. Okay, we have the sway mechanism. And obviously we have the points of interest, Q and R. Okay, these are the intersection points. Q is, you can see here, Q corresponds to part sway and combined together. So Q, part sway, plus combined mechanisms. When we say both of them, this point Q corresponds to what we call an over collapse. An over collapse. Why is it an over collapse? Why is it an over collapse? Apart from the fact that it's a part sway and combined together, why is it an over collapse? Why is it an over? Look here. This is the combined, and this is the part sway. Hello?
I'm new student.
Sorry?
I'm new student.
You're new?
Yeah, yeah.
We started at, did you know we start 11 o'clock?
I have an appointment for the BRT card. That's
Okay, it's all right.
Sorry.
Yeah, you have a lot of catching up to do.
Okay, thank you.
Okay, it's welcome. So we have we have combined mechanism. Were you following online before?
Yeah, yes.
You were?
Yeah,
You were
yeah.
attending online?
Yeah, yeah.
So we have combined here, look at here, we have combined and part sway, isn't it? So when the two take place together, you can see that we have hinges at C, D, and E, but we're also going to have a hinge at B when you put them together. So you're going to have 5, which is more than that we need, because we said we need only 4 for total collapse. So when you put these two together, you get an over collapse. Okay? You get an over collapse, right? Which is not something that you, it doesn't give you the critical load, but that Q, as I said, represents a case where you have 5 hinges forming, and therefore it's an over collapse. And the same thing happened here for R. Okay? For R, we have sway and combined together. So R, we have sway plus combined mechanisms. And for the same reason, it's an over collapse mechanism. Okay? If you want the coordinates of Q and R, coordinates of Q and R, it's easy. For Q, you can see that for Q, we have V is 35. So what you do, you take the V equals 35 and put it into the equation to give you V. Is that clear? Yeah. So take V equals 35 and put it into the equation. So we have 5H plus 8V, 835, equals 380, which gives H if you want to check the answers. Is that 20?
Yeah.
Yeah, 20. So we've got H is equal to 20, so Q corresponds to 20 and 35, the coordinates. Okay, so Q is 20, 35. So this load combination, when H is equal to 20 kilonewtons and V is equal to 35 kilonewtons, when the two together here are together, you get an overcollapse mechanism. Okay, which is not something you want, because it doesn't give you the most critical, because it's an overcollapse. You have more hinges than you actually need. Similarly, if you want the coordinates of R, okay, you need to take the H here, okay, So H is 40 for R. Okay, for R, H is 40. So you take 40 and H40 here, and you get V from the equation. Okay, so H is 40. So you have 5H plus 8V equals 380, which gives V 22.5, which gives R, therefore R is 40 and V 22.5. So this load combination, when H is 40 and V is 22.5, will give us an overcollapse where sway and combined happen at the same time. Okay? So this interaction diagram gives us all the possibilities. So any load combination inside, for example, if I take H20 and V20 kilonewtons, it will not give me any collapse, it will be safe. Okay? And then any load combinations on the border here give you one of the mechanisms that we have analyzed. Okay?
What about the critical one?
That's the critical ones. That's what I'm saying. So any load, so say you take H 10 kilonewtons, okay, 10 kilonewtons, and V 35, you get a critical, your critical mechanism will be pass wave. Okay? If you take, I don't know, if you take H 40 kilonewtons and V 10 kilonewtons, which is this point, that will definitely give you a sway mechanism. And that will be your critical one. Okay? So your critical mechanism is one of them depending on the load combination. Is that clear? Yeah? Okay? I'm going to show you now how to plot the bending moment diagram for any of the mechanisms here. We haven't got time to do all of them. I'm going to show you, for example, how to do it for the collapse mechanism, for the combined. It will be the same for the others. All right? Is it too dark?
Yeah.
Let's do it. Is that better? Yeah. So, bending moment diagram. Bending moment. So bending moment diagram, have you any questions? Is that clear? Yeah? So, so the bending moment diagram, let's do it for, okay, let's do it for combined mechanism, for example. So I'm going to take a combined mechanism here, yeah, a load combination that falls within this range, and I'm going to plot the bending moment diagram for that. Okay. So let's say, for example, let's take H30, for example. So I take this point. See that? Yeah. So for example, for H equals 30, what would be V when H is 30 to give me a collapse mechanism? Substitute. Yes? So we have 5H plus 8V equals 380. Can you work out V for me, please? Is it 28 point? 28.7. 75. Okay, 28.8. So V is, H is 30. So this load combination of H and V will give me a combined mechanism, definitely. Okay, for the interaction diagram. Right? So I'm going to plot what is the bending moment diagram for this collapse mechanism. And you can do it for any collapse mechanism here. You can take any load combination. You go back to the combined mechanism in question, and you plot the bending moment diagram. Is that clear? So let's do it. Now, where is the combined? Okay, this is the combined mechanism. Okay, this is the combined mechanism. So let me do it here. Okay, please follow this carefully with me, please. Okay, so at A, we have a anti-clockwise moment, MP, right? So we have anti-clockwise at A, MP. At B, we don't know yet. That's unknown. What we know that at C, we have got MP. So we have anti-clockwise MP and clockwise MP for equilibrium. Then at D, we have MP, that's clockwise. Okay, that is clockwise there. So I have clockwise here, MP. And you can see here we have anti-clockwise, so we have MP there. And finally at E, we have anti-clockwise MP. Anti-clockwise MP. That's why it's very important when you draw your collapse mechanisms, you show the direction of the moments.
Shouldn't the MPs at C?
Oh, sorry, no, you mean here at C.
C,
Yeah. Yeah.
It is the same. And then the D.
We don't know B yet, but these are okay, yes? Okay? From the collapse mechanism, we know the direction of the moments, okay? Clockwise, anti-clockwise, anti-clockwise, clockwise, clockwise, anti-clockwise, anti-clockwise, as we have done here. Clear? Yeah? Now, we don't know B. We don't know B. So, if you don't know the B, that's unknown, okay? So if you don't know the moment at B, you can assume an arbitrary direction, any direction that you want. For example, I'm going to assume MB is in this direction, okay? So I'm going to assume MB in this direction. If we get a negative answer, we know we made the wrong assumption, which is not a problem. Then you can rectify it, okay? In order to plot the bending moment diagram, in order to draw the bending moment diagram for this frame, I need to find what is MB. I need to find MB, right? How do we find MB? How do we find MB? I think we can start with column ED. We can start with column ED because we know the moment at E and we know the moment at D. So if I start with, if I take a cut at D, I can determine the horizontal reaction at E. And then from that, I can determine the horizontal reaction at A, and therefore the moment at B. Okay? So if we want, step one, we take the equilibrium of D. Okay? In other words, we take a cut at D. So we take a cut at D. So this is column ED. We have anti-clockwise MP. We have anti-clockwise MP. The height is 5 meters. We also have a horizontal reaction HE. So we have a horizontal reaction here. There is also a vertical, but we don't need it. Okay. So we take moments about D. Moments about D. Clockwise moments about D, we have MP and MP. So we have MP plus MP, that's clockwise, equals anti-clockwise, we have HE times 5. HE times 5, which gives 2MP equals 5HE. So therefore, HE will be 2 times 50 divided by 5, which is 20. So the horizontal reaction at E is 20. Okay? Now, so here we have the horizontal reaction here is 20. The horizontal force H is, what was the value taken? Sorry? Is it 40?
Yeah.
No, 30. I think we took 30. Yeah, 30. So here we have 30. So therefore, if this is 20 and this is 30, so what's the reaction at A for equilibrium? 10. So the horizontal reaction. So therefore, here you can say therefore HA is 30 minus 20 equals to 10 kilonewtons. Now we take the equilibrium of this column here. So take a cut, step 2, take cut at B. So we do the equilibrium of AB. So this is column AB. Okay, this is column AB. We have, at A we have anti-clockwise MP. Then we have chosen MB in this direction, we don't know. And obviously we have a reaction here of 10. And this is 5 meters. So we take moments about B, clockwise about B we have 10 times 5 equals, anti-clockwise we have MP plus MB. 10 times 5, 50. MP is, what is MP? 50 plus MB. So what is MB? 0. It just happened, pure coincidence, that in this case we have MB 0. If I have taken different values here, if I had taken different values for H and if I had chosen different values for H and V, obviously you get a different value here for MB. Okay, it just happened that MP is 0. The main thing that it is less than MP, that's the main thing. So yield condition is satisfied. Okay, that's the main thing. Is that you don't get a value greater than MP. Now we are going to use this to draw the bending moment diagram for the frame. Okay, so going back here, what we have 0 and 0. Okay, so we know the moment is MP everywhere except at MB, where we have 0 moment for this particular load combination, which I'm going to plot here. So, bending moment diagram. So now we do the bending moment diagram. Look here. Can I have attention? Look, when you draw the bending moment diagram, always plot the values on the side of the member where there is. How do you plot it? When there is tension. So if you look at A, where is the tension? Left or right? Here? Yeah, that's it. So once you know where the tension is, then you can plot on that side where the bending moment is. And this is the only way you can get your bending moment diagram correctly annotated. Okay, so let's do that. So I'm going to take this here to draw the bending moment diagram for the frame. So we have MP at A, and it's on this side. That's MP. We have 0 at B. Then we have MP on this side, so we have MP here. Okay. Then I have MP on this side. Then I have MP at the top, so it's perpendicular here. MP. Then we have MP at the bottom, which is perpendicular, and we have MP which is perpendicular again, and we have 0 there. Now I'm going to join, okay? So you join these two together, and you join this and this one here, and you join this one to A, and finally you join these two together. And this is the bending moment diagram for the frame for this particular load combination of H and V.
Can you
Okay?
explain that again?
Sorry?
Can you explain this again? How?
Okay, you plot, you know where the tension is,
Yeah.
so you plot the moment on the side of the tension.
Yeah.
So for example, here you've got MP on the left,
Yeah.
okay, etc. So you've got MP at the bottom,
Yeah.
MP at the bottom, and MP at the top, there, and MP on the right, on the left, and then you join together for each member. Okay? Right, and that's the bending moment diagram for the collapse, for the combined mechanism for the particular combination of H30 and V28.8. If you change the values of H and V for the combined mechanism, you will get a different value of MV here, but the diagram, the steps are exactly the same. Is that clear? Yeah? Any questions? Have you got any questions? Any questions? If you read if you go to Aula, there is like a post-session tutorial for you to try. And what I've asked you to do for that particular tutorial question is to actually resolve the same problem here, but this time with H applied at D. So you can try and work out the solution when H is not at B, but it's actually applied at D to the right. And see what difference it does make. Try it. If you get it wrong, it doesn't matter, because Friday I will upload the solution, so you can look at it. Okay? But that's the post-session. And next week we will look at asymmetrical frames, when you have a frame with asymmetrical geometry, but also when the MPs are different. So you have different MPs and different geometry. All right? Any questions? Okay, so thank you very much. I'm going to stop the recording now. Thank you.